neonatal seizure detection, a deep learning approach. So I'm going to talk a little bit about the history of automated neonatal seizure detection, a little bit about the medical background, and then I'm going to talk about the journey we took to creating the deep learning approach that we developed. So this work was done probably between 2015 and 2020. So kind of contextualize it within the deep learning world that way. Neonatal seizure detection algorithms have actually been around since the early 90s. They've been around for a long time. And early works really applied heuristic thresholds to quite straightforward features. Where the kind of engineering work really started was when they started doing more and more advanced feature engineering, coming up with more niche and task-specific features. Then in the early 2000s, machine learning took over. And of course, there's an intrinsic link between this idea of neonatal seizure detection feature engineering and just generalized signal feature engineering and machine learning. So from 3 decades of research, we kind of had to decide where did we want to go next. So we figured that the idea of applying deep learning and trying to create a new paradigm was where we wanted to go. And our hope was that it would be a step change from the machine learning and the feature engineering that still goes on today. Those are still very active research areas within this field. So what are we trying to do when we detect seizures, and specifically neonatal seizures? So first of all, the neonatal period is the first month of life really after birth. And in this period, seizures represent a neurological emergency. They're often the first sign of an underlying serious brain issue. So it's very important that we detect them and we know if they're happening in infants. This is also the time in your life where you're most likely to have a seizure. So there's a much higher burden of seizures in this age group. The problem with detecting these events is that they are typically subclinical. 66% of neonatal seizures have no physical signs or symptoms, so we can't look at an infant and easily say this infant is having a seizure event or not. Instead, what we use is the electrical brainwave. So we use electroencephalogram signals. These are EEG signals, and this is the gold standard for detecting neonatal seizures. You can see this infant that I'm showing on the screen has multiple different electrodes attached to their brain. So we look at the signals in different areas of the brain specifically. So here I have a multi-channel signal where each channel represents a different region of the brain. The even numbers, I think, are the left hemisphere. The odd numbers are the right hemisphere. And what I'm actually showing you is what we call a bipolar montage. So it's the difference between the energy in the F4 channel and the energy in the C4 channel. So literally the subtraction of the voltage in F4 from, or C4 from F4. So it's quite a straightforward equation. And that's how we get these signals. And I'm actually showing you a window that has a seizure in it. So this would be annotated by a clinical expert as being a seizure. It's hard for me to say that it's a seizure, but I have an annotation that tells me that it is, which is made by a clinical expert. So what we're looking for when we're searching for a seizure is a rhythmic evolving pattern that lasts for at least 10 seconds and is greater than 2 microvolts in energy. So very low signals, which leads to potential noise, and also evolving patterns. How do you detect evolving patterns? If you're a signal processing engineer, you might think, okay, are these stationary or not? Lots of questions there. But really, if I showed you this image and said, what you're seeing in the red square is a seizure, and what you're seeing outside it is not seizure, you might say, well, they're easy to detect. But what you can notice is that an infant can have some channels that don't display seizure symptoms and other channels that do at the same time. That complicates our data collection. And what I'm not telling you is that EEG signal is susceptible to artifacts, whether they be electrical artifacts or physiological artifacts. Here I'm showing you an artifact that is either from muscle or potentially it's from the heart rate, it's from the ECG. Here I'm showing you an artifact that is more than likely from the respiration of the infant. So these are rhythmic patterns that are not evolving and that are not due to seizures in the infant's brain. So that makes things a little bit more complicated. Okay, so I think we have the medical background now, I hope. What I want to describe to you now is the machine learning baselines that we want to compare our deep learning algorithm to, because the machine learning baselines in this field are actually extremely powerful. I shouldn't say actually, they are extremely powerful, and they're quite reliable, and they deliver very, very good results. And what these machine learning baselines typically look like is they process multi-channel EEG here on the left. Then they do some feature engineering. So they extract features from each channel individually. These have been worked on by experts, really, really brilliant minds. And the thing is that this feature engineering step is optimized on its own. So the features are selected, they're transformed, maybe they are normalized, different things applied to them. And this feature engineering step requires a lot of brilliant engineers and a lot of thinking. Then what we have next is we have channel feature vectors. So each channel of the EEG will now be represented by a certain set of feature vectors. That's the output of this feature engineering stage. Then we have a classification algorithm. The algorithm that I compared my work to was a support vector machine algorithm. And again, the algorithm is trained, validated, and selected in a kind of optimized fashion just within itself. So it's not connected, it's not a holistically optimized pipeline. Instead, the algorithm and the feature engineering are optimized separately. So what you'll get is you'll get individual channel vectors of features. They will be passed through a trained algorithm. You'll get some prediction based on each channel. And then in EEG seizure detection, if any one channel is in seizure at any time, that is considered to be a seizure window. So we label all of the channels as being seizure, or we say that the baby temporarily at that time has a seizure event occurring. So we can, select or we can do some kind of a maximization to say, are any one of these predictions higher than a certain threshold? If so, the infant has a seizure. We can do moving average filters. We can do some post-processing. And this pipeline has been developed over many, many years. And one limitation it has is that neonatal staff would never differentiate the channel the seizure comes from. They don't care. They just care if there's an event happening or not. So when you go to train a channel specific algorithm like this, an SVM algorithm, basically our research group had to ask them to go out of their way to specifically define this channel that a seizure was occurring in. It's something that clinical staff don't have training in, and it represents a huge time burden. So when this SVM algorithm baseline was being compared, they only had a small subset of an overall training data set to train on, because only a small subset of seizure events actually had this channel specific labeling. So that's something we had to take into account when we were moving to deep learning, because in deep learning, algorithms are very data hungry. So maybe it's not as relevant for some machine learning algorithms, but in deep learning, the algorithms are quite data hungry. So we had to kind of maybe find a way of utilizing the data more efficiently. So this pipeline works well and it's very effective, but what our hypothesis was if we could somehow combine the feature extraction and the classification into one end-to-end optimization routine, surely there is some improvement we can get there. So instead of having these two isolated optimization steps, we could create one algorithm which goes from minimally processed EEG, i.e. not transformed to features, to predictions all in one go with the same backpropagation algorithm in this instance. There's potentially room for improvement there. So the question at the beginning of my work was, well, what does that minimal pre-processing look like? What does that basic representation look like? So how do we learn from neonatal EEG that has not been transformed into an informative feature set? So we start out with a temporal signal, excuse the quality here. This is a signal of EEG that is 30 seconds long. You can see that the voltage is quite small, and this is what it looks like. So we looked at transforming these signals to spectrograms, which is basically where we look at the frequency distribution over time. And this gives us a 2D image. And in 2015, when I started this work, when we thought about deep learning, well, we said, well, it has to be applied to 2D images. This was, 3 years after Alex met. So we kind of thought we gotta have images somehow. So we looked at transforming the EEG to a spectrogram. We also looked at weighting the frequency components in the spectrogram, either through static or trained weights. There is an understanding, well, it's a hypothesis, in this field that the lower frequency bands have more information. So we looked at weighting the lower frequency bands more heavily with a kind of human engineered filter bank, which I designed, wasn't the best, but then we also looked at weighting the filter banks with a trained filter bank. So the training of that filter bank could become part of the deep learning algorithm as well. These were our 3 different image representations. And then we said, for the hell of it, we'll also just put in the signal as it is and consider it to be like a 1D image and try to train that too, see what that looks like. And our results were quite interesting because what we ended up seeing was, if you look at the representation of the spectrogram, we were getting okay performance with very little optimization, very little algorithm development, very little architecture development, just looking at the internal or the input representation at this point. There wasn't much difference between the spectrogram with the static filter bank, and the spectrogram with the learned filter bank. But when we looked at the temporal EEG signal, so feeding it in as a temporal signal, doing almost no transformation other than a little bit of noise reduction by having a notch filter at 50 hertz and removing kind of low frequency and high frequency bands that we didn't think were that important, we were getting close to 89% AUC, area under the receiver operating curve, which is quite far from our machine learning baseline. That SVM algorithm had 96.6% AUC, but out of our options, temporal representation seemed like the best option. Now, looking back 6-7 years later, I can say that all of these probably deserve research too, and probably deserve some more exploration. But at the time, we figured that this was the path we wanted to go down, this temporal representation. So this validated a few things for us. Deep learning can extract informative features from minimally processed EEG. We don't need those engineers' feature sets. Temporal signals appear to give the best performance, but again, these aren't very thorough experiments. They're just initial experiments. The data, the computational power, and algorithms are now available to develop deep learning-based neonatal seizure detection algorithms. So we are ready to kind of progress this further and move forward with this research. So the question then was, can deep learning outperform the current state of the art? What do we need to do to get this deep learning algorithm to outperform the current state of the art? And what I chose to experiment with was a fixed kind of architecture with some dimensional change. So I created an architecture which had what I called feature extraction blocks. So these were fixed blocks of 3 convolutional layers, all one-dimensional convolutions, because we're working with one-dimensional signals, separated by rectified linear units with what I call small sample-sized filters. So each convolutional filter is just looking at 3 samples from the previous layer. The idea of using small sample-sized filters came from the audio domain. So you could imagine that some of the advances in the audio domain at this time, I was repurposing for use in my domain as well. And the point of kind of doing this architecture exploration was that in the past, the PhD student or the researcher's time would be spent on feature engineering, whereas now I could put my time into architecture engineering because I didn't need to worry about the features anymore. So I had 3 convolutional layers and average pooling. And the average pooling could take a stride of 1, 2, or 3. You could just think of stride of 1 as being less downsampling, stride of 3 as being more downsampling. Then I added a classification block, which we'll come back to in a second, to classify inputs into seizure and non-seizure. And I created this architecture where the input was raw EEG. I had n number of these feature extraction blocks. So I think I went from 1 to 5, so 1 or 2 or 3 or 4 or 5, and I varied the stride here. So I did more or less downsampling as I progressed. This was then followed by a classification block. My classification block is different to those normally seen in deep learning algorithms. Usually you have like a multi-layer, or sorry, like a perceptron layer. So you have a fully connected layer where all inputs or all nodes in a layer are connected to all nodes in the previous layer. That's really resource heavy. So instead I used what I call a fully convolutional architecture, where I just had 2 convolutional feature maps, 1 to represent seizure, 1 to represent non-seizure, and the energy between the 2, so a comparison of the energy between the 2, you can see I have a softmax. So anytime you have a softmax, you're basically weighting one against the other, and that would tell me the probability of seizure or non-seizure. So this was my architecture. This is a better comparison of that architecture with the traditional algorithm. So we both take an 8-second window of EEG, sampled at 32 Hertz. We both pre-process using the same simple filters, high pass filter, low pass filter, notch filter, and then we kind of differ here. So the feature extraction step and the support vector machine step are put in before post-processing, whereas I just have this end-to-end algorithm where I have what I call an increasing receptive field. Each sample in the subsequent layers sees more and more of the input. You can see here the blue sample here sees 3 samples in the input, whereas the red sample in the second layer sees a much wider receptive field in the input. This is kind of theory from deep learning algorithms. And what we found was that we could outperform traditional machine learning baselines. This is the traditional machine learning baselines, even with very small algorithms. This is an algorithm that has 1 of those feature extraction layers. These all have 2 of those feature extraction layers, 3, 4, and 5 feature extraction layers. You can see the number of parameters increasing, the number of parameters here in each circle. They increase as we go to the right. Then I looked at the pool strides. Pool 1 is very little downsampling. Pool 3 is a lot of downsampling. And I saw that the more pooling I did, the more downsampling I did, actually the better the performance. And I believe that is linked to this idea of receptive field. Next to each square, I have the receptive field of each of these data markers. Here, the receptive field is very, very low. So even though we have a massive network of 45,000 parameters, a huge network, we actually have very little predictive power. Well, we have over 97% AUC, but relatively very little predictive power. Whereas here, where we have this 25,500 parameter network, but we have the widest receptive field we can possibly have within the constraints of my experiment, we actually have the best performance. But importantly, all of these networks outperform the machine learning baseline. So another fact that I forgot to point out here, and I promise I'll be wrapping up then, is the algorithm that I designed no longer needs to predict based on single channel EEG. So I actually apply this algorithm across all 8 channels. I give the network an 8-second window of EEG, a label of either 1 or 0. If I give the label 1, I'm telling my algorithm that there's a seizure somewhere in here, but I'm not telling you where it is. Or this could be a generalized seizure example where every channel has a seizure. So I'm giving what I call not strongly labeled data, because the labels aren't strong. These are weakly labeled data samples. Somewhere there's a seizure, I'm not telling you where. And by doing that, I can use an entire data set of EEG, because this is how clinicians grade their EEG. They say seizure or no seizure. I'm not telling you where. So I could use vast amounts more data, but I have these weaker labels. But I actually found that gave me vastly improved performance. So that was the kind of algorithm we went forward with. So through architecture optimization, it has outperformed previous baselines. And through that architecture optimization, I came to the understanding that receptive field was an extremely important factor in the architecture and something that we should be mindful of. And the other thing, which maybe doesn't seem too great to you guys, but I was one of the first algorithms at the time to do this, use weakly labeled EEG seizure information to train an algorithm because of the architecture that I set up. So I think that's kind of all I have time for. The one thing that we also did was we applied these learnings to preterm data, which is a much more challenging data research area, because the data sets are smaller. EEG morphology varies with gestational age, because preterms could be all the way from 24 weeks gestational age to 38 weeks. So it's a huge variety of developmental change. And the seizures are more focal than those found in term EEG. So they can be more isolated to single channels. But using knowledge and kind of improving our algorithm and improving our training routine, we were able to create reliable and robust classifiers for all age groups. And then we also looked at translating these algorithms using those receptive fields to kind of help understand why algorithms were making decisions they did. So we were able to take seizure examples. So this is an example of a correctly labeled seizure. And using this kind of 0 to 1 marker, look at the patterns which were more likely to result in seizures. So this pattern told my algorithm it was a seizure, this pattern too, and this pattern too. So we could kind of isolate patterns, same for non-seizure. And then we also looked at synthesizing EEG. So if we can do gradient descent, which is the algorithm for training deep learning algorithms, we can theoretically do gradient ascent, which means we're basically taking a randomized input signal and optimizing it for non-seizure and optimizing it for seizure. So we're creating fake EEG, which could potentially be used for training or something else. So overall, it was novel to know that we could do this with deep learning. The path we took was to do it with temporal EEG, which might not have seemed as the obvious path, but from our initial experiments, it seemed like the right path. And kind of my time was spent on architecture exploration and in architecture optimization, one might say as well, instead of, I guess, the more traditional areas of feature extraction, feature optimization, and feature engineering. Yeah, so that's it. Thanks, guys.
Thanks very much for that, Alison. That was great. Okay, lads, do we have any questions? Okay, I'll go first if nobody's speaking. Okay, look, that was interesting. I guess I would have been familiar with a lot of the terms in it. Haven't worked in the area, but in terms of, say, your synthetic data generation.
Yeah.
Well, I have two questions. What was the quantity of data that you were used to actually train the model, the raw EEG you had available to yourself? Like, how much EEG are you talking?
So to train term models, we had over 850 hours of EEG, multi-channel EEG, 8-channel EEG. So that's a lot of data. And
then did you assess what the minimum quantity of data available was for actually getting a performant model?
That's a good question. No, we didn't do that. And it is actually a limitation, I guess, of deep learning. Well, the deep learning solution that I developed, because the only currently publicly available the only publicly available data set of neonatal EEG is 112 hours. And it has about 35 seizure babies and similar amount of non-seizure babies, which I've kind of done a couple of experiments briefly, not gone too in depth, but it's not enough to train the model to any reliable degree. So that is a limitation. I'm still relying on these vast privately held data sets. So no.
Okay. Good. And the synthetic data you generated, was there an evaluation performed of the quality of the synthetic data?
No, that was like I was doing that while I was working full time, so it wasn't the best done work in the world. But I just thought it was interesting because this idea that we could potentially use this network to synthesize what look like different EEG patterns or look like different seizure patterns would be interesting. If I had more time, I would have done something like taken the existing machine learning algorithm, the SVM algorithm, and basically said, does the SVM algorithm think this look like a seizure? Does the SVM algorithm think this look like a non-seizure? And basically said, is it like a crazy artifact of deep learning? And then the next step would be to say to like Geraldine Boyle, like experts in the hospital, what do you think this looks like? Does it look anything like EEG or anything like, seizures? But I think it's just like a kind of, it was just an experiment that really wasn't, I would say, super supported. It was kind of showing that it's potentially possible, but I don't know if we're doing it the right way.
Okay, final question. So you mentioned the preterm EEG is higher, more noise, higher variance between the signals because it's more complex. Now, is the variance limited to the gestational age, or like, so like if I have or what's the kind of how do you collect?
Yeah.
Organize that data is my kind of question.
Yeah. So in the end, the algorithms that I developed were gestational age specific. So I did end up having a solution where actually you have to know the gestational age of the infant, and based on that, you select a particular algorithm to use. That was the best performing routine that I had. So there is that much variation between the gestational ages. Like you could imagine it at 24 weeks, at 24 weeks gestation, if you actually look at an infant's brain, it won't even have the folds that we imagine to be. Like, it's so different even structurally. The issue with that gestational age algorithm training is that there's so little data available. Like, I really didn't have that much data at all available to me. And of the data that I had available, there was quite rare seizure events. Like, I had one gestational age range that was, let's say so initially when I started working on this work, people were splitting it into 6 gestational age groups. 24 weeks, 25 weeks, each week was almost a new group. And there was one group, and the only seizure example I had in that was one 40-second seizure from one infant. And I was like, really, we don't have enough data to support this much kind of segmentation. We can't support it. So that's why I chose to combine the groups. So we had a extremely gestation or extremely preterm 24 to 27, very preterm, they're still extreme words, very preterm 27 to 30, and then moderately preterm 30 to 32. And that was actually due to data constraints more than anything. So I suppose an important difference that I can see is the gestational age groups, this is a group specific classifier that we developed, a group specific classifier we developed, and a group specific classifier we developed. But I don't know if there's much quantitative analysis on how different the seizure is, like from a medical point of view, how different the patterns are. That's kind of more what I've heard from talking to people.
Oh, that's really interesting, because I mean, you combine that with your synthetic generation and create
more.
I mean, that's the direction I would go in anyway. Okay, that's
Thanks,
great.
Rory.
Anyone else have any questions?
Hi, Alison. I just have one question about the neural network architecture. I think I think it ended with max pooling layer followed by softmax layer.
Yes.
Did you use any densely connected layers in between?
Great question. No, we didn't at all. So this is our last convolutional layer, let's say, of the feature extraction section. Then, as you said, I have a convolutional layer which creates two feature maps. Then the max pooling, average pooling thing is actually to get the average value across the time domain of seizureness and non-seizureness. And I kind of replicate previous post-processing where I say, well, if there's a seizure in any one of these channels, then that's a seizure example. So I basically take the max across the time domain, and that's why I use max. No, I have no fully connected layers here. One reason for that is because I'm using quite small sample inputs, and I basically didn't want to have really highly parameterized networks. So I started working with these fully convolutional networks, and it basically meant my network is X amount times smaller than it would be if it was kind of the traditional VGG architecture where you're finished with a fully convolutional layer. So no, and it's great because this smaller architecture, or maybe this fully convolutional architecture, means that we've actually implemented these networks on Android devices and embedded systems devices on the edge. So it's a much more appropriate algorithm to be putting on kind of in low resource settings. Whereas maybe if we had more data and used a fully connected layer at the end with more parameters, we could have maybe gotten even better results. I'm not sure.
Okay, thanks. Cheers.
I think Christian has a question.
Yeah, if I may. Yeah, you showed us the receptive fields there. And I suppose if you have a convolution layer for image processing, the reason for these, of course, is that objects are localized in space. And also for audio processing, everything is localized in time, I suppose. But for the EEG seizures, that might not necessarily be the case. So I'm wondering, how does that compare to the engineered feature extraction methods or algorithms, or how is that motivated in terms of applying a convolutional approach, except for showing the 98% as everybody does?
Yeah, that's a good question. So you're saying that like often the features that you develop to detect seizures, when you're engineering a feature, you will say, is this pattern repeated? You know, you're looking for repeating patterns. So you are looking over a long time scale. So like if
that would be in the frequency domain that would be located, but you're looking at the spatial domain here and you're localizing things in the spatial domain. And I would expect that your spectral analysis, apart from the fact that converting everything into a picture and then running it through an image processing CNN doesn't resonate with me. But you look at the time domain, not at the frequency domain, right?
Yeah.
So when you have a repeating pattern, the receptive field would be limiting themselves to looking at parts of that only.
Yes, but as you go to deeper and deeper layers, the receptive field covers almost the entire input. Like here we have a 172 sample receptive field, and if you multiply 32 by 8, what do you get? Maybe 100 or 256. I can't even remember how many samples are in the inputs, but this is a good percentage of the input window. So we're just looking at 8-second windows, and 172 samples is a high percentage of that input window. So yeah, I see your point, but then if I look at what the signal is, or like what parts of the signal are highlighted by the algorithm for the reasoning that it made its decisions, I can see that there are repeating patterns are highlighted by the algorithm as the reason that it made its decision. So maybe I can't explain the mechanism there, but I do think it must be finding these evolving repeating patterns. I suppose one limitation that I didn't mention is a limitation of neonatal seizure detection is that, neonatal EEG is a non-stationary signal, and even when you look at very, very small windows of that signal, it's considered to still be non-stationary. So every time we do a frequency transformation, we're making kind of we're putting a human-induced bias on it. So that's potentially a limitation. Well, there's ways you can get around that, but it's a potential limitation there. And I suppose overall, sorry, Marie, overall, I would say that like what this work was trying to do, and maybe it undermines my role in it because maybe it just means that I know nothing, but we were trying to remove all of those human-induced biases. So like every time you decide what feature to extract or decide how to represent EEG, you're theoretically viewing the signal through your lens that you make a decision about.
But when you architecturally decide on a convolution, you are also making a structural assumption. That's what a convolution is at the end of the day.
True. Yeah, about local importance. Yeah, exactly. Yeah, and local relationships. Yeah.